Hi guys, this is Dr. G, and in this video we are going to talk about Organic Chemistry Chapter 18 from John McMurray textbook. And in this chapter 18, we are going to talk about ethers, epoxides, thiols and sulfides. So these are the learning objectives for this chapter. But in this video, we will be specifically talking about 18.2, which is basically preparing ethers, or the reactions that we can use to synthesize ethers. Alright, so ethers are basically organic derivatives of water. So water, of course, has an oxygen atom and two hydrogen atoms. And on the oxygen, you have two lone pairs, right? So when it comes to ethers, these hydrogens are replaced by R groups. These hydrogens are replaced by R groups. So what you have is an oxygen with two R groups. These R groups could be the same or it could be different from each other. Okay, it doesn't really matter. Okay, there could be symmetric ethers or asymmetric ethers, but basically this is how ethers look like. They are organic derivatives of water. Why? Because the two hydrogens of water are replaced by organic groups. And in this slide I have a few examples for you guys. You can also take a look at them. These are directly from your textbook. So you could have symmetric ethers like this one, or you could have asymmetric ones, or even you can have cyclic ethers. And basically the oxygen atom on ether is very similar to the oxygen atom on water. So it is sp3 hybridized, and the bond angles are basically approximately close to the tetrahedral bond angles. The most important thing about ethers is that they are very stable, and therefore they are mostly unreactive. And because of that, you can see that in organic chemistry, throughout organic chemistry, we use ethers as very useful solvents. They are very useful solvents. That is one thing that you might want to remember. They are very useful solvents because they are relatively stable and unreactive. Alright, so with that, we are going to talk about synthesis of ether. Industrially, the synthesis of ethers is achieved by using alcohols. Industrially, the synthesis of ether is achieved by reacting alcohols with sulfuric acid as the catalyst. Okay, so basically we are using a very strong acid such as sulfuric acid as a catalyst to synthesize ether from alcohols. Of course, alcohols have an organic group attached to an OH. So what we do is we basically acidify these alcohols by a strong acid, specifically sulfuric acid, so that you will get a hydrogen onto the OH group, so making the OH group into a water molecule. So it is a very good leaving group. And then another alcohol will attack the previous alcohol. Okay, in here this alcohol is attacking, this molecule is attacking the protonated alcohol, giving you an ether in the process. So this is the ether that you obtain. Okay, so this is an SN2 reaction. If you remember SN2, okay, to have SN2 so to have SN2 reactions, you are required to sorry about that. So you are required to have primary alcohols. Okay, so that is a limitation. Of course, that is a limitation. You are required to have primary alcohols in this reaction, which means the alcohol carbon has at least two hydrogens. Okay, so that is how you get primary alcohols. Okay, so the alcohol carbon should at least have two hydrogens. So you are only limited to primary alcohols, and also the alcohols that you get are symmetric. The alcohols that you get are symmetric. That is also another limitation. So let's say you used ethanol, or let's say methanol. Okay, so you are using methanol, and you use sulfuric acid for the reaction. Okay, and then the alcohol that you get has two methyl groups as R groups. Two methyl groups as R groups. Okay, so you're getting very symmetric alcohols because both R groups are the same. Okay, both R groups of your ether is the same. In this case, it is a methyl group. So you only get symmetric ones. Okay, if you want an asymmetric ether, this is not the way to do it. Okay, and also you can only use primary alcohols. You can only use primary alcohols. Okay, so those are the two limitations of this reaction. All right, so let's go to the next slide. The second reaction that we are going to talk about is called Williamson ether synthesis. This is actually a very significant reaction for your reaction book. Okay, so this Williamson ether synthesis also involves SN2 reaction. So this is also uses SN2 mechanism. Okay, so very similar to the previous industrial method that we discussed a few minutes ago. Okay, therefore you're going to need certain conditions for this reaction. Specifically, in this reaction, you are going to need an alkoxide ion. Okay, an alkoxide ion. You guys already know what are alkoxide ions. Okay, so you can generate an alkoxide ion from alcohols, of course. Okay, you treat an alcohol. This is your alcohol. Here is your alcohol. You treat your alcohol with a strong base such as sodium hydride. Okay, so you use a strong base such as sodium hydride to generate the alkoxide ion. Once you have the alkoxide ion, you will use a primary alkyl halide. Okay, you will use the primary alkyl halide and then generate the ether you want. And then you will generate the ether you want. Okay, so that is how you do it. This is how you do it. Let's take another example. So let's say we are going to make an alkoxide ion from ethanol. Okay, so let's say we have ethanol, CH3, CH2, OH. Here is our ethanol, and then let's use sodium hydride, a very strong base, and then a solvent. Okay, THF seems good, and then what you get is an alkoxide ion, CH3, CH2, O minus. Okay, so this is going to be your alkoxide ion, or you can say this is your nucleophile. This is your nucleophile. This is your nucleophile in the SN2 reaction. Okay, and for this alkoxide, you are adding a primary alkyl halides. Let's use methyl iodide or methyl chloride. Okay, so let's use a different color. Let's go for green. Okay. Right, so make sure to use only primary alkyl halides. Okay, and then you will have a SN2 reaction. Okay, you will have an SN2 reaction. You will have an SN2 reaction where, you know, between the nucleophile that we just prepared using alkoxide ion and the CH3I, and then what you get is this CH3 O CH2 CH3. This is the ether that we get. And here's the good thing about this reaction, guys. You don't need to, I mean, you don't always get symmetric ethers. You can get asymmetric ethers. That is a significant thing about this reaction. So as you can see, for the ether that we made, we had a ethyl group and a methyl group. So this is not symmetric. So you can synthesize asymmetric ethers from this reaction. That is an important thing to remember. But still, this reaction has a limitation. Why? Because you need a primary alkyl halide. You need a primary alkyl halide. That is still a limitation. Because, I mean, we are using SN2 reaction, so you need to have a primary alkyl halide where the iodide is the leaving group, and then the nucleophile will attack that carbon, the CH3 carbon right here. All right, let's go back to the lecture note. All right, so the next reaction that we are going to talk about is a silver oxide catalyzed ether formation. This is also a very unique reaction. This is also a very unique reaction where you use silver oxide as your catalyst. Okay, so silver oxide is your catalyst in this reaction, and then you also need an alkyl halide. You also need an alkyl halide. Okay, so in this slide I have given you the reaction between glucose and methyl iodide. Glucose and methyl iodide. In this reaction, what happens is that the methyl group will be substituted to the hydrogen of the OH group, giving you 5 ether groups. Okay, so this is also just like the previous reactions, but only difference is that you're using silver oxide. But this is not as common as the Williamson ether synthesis. All right, so let's see if you could do this worked example. So if you are watching the video, I want you to pause the video now and then see if you could do this by yourself. All right. Okay, so in the first example, what we have is methyl propyl ether. So what you want to synthesize is a methyl propyl ether. Okay, so you have 3 carbons on one side and only 1 carbon on the other side. Okay, so this is a methyl propyl ether. So to synthesize this, you have 2 choices. You can provide the, you can add the, I mean, this has to be done using Williamson ether synthesis. So you know that, we use an alkyl halide and an alcohol, okay, to generate the alkoxide ion. All right, so you can get the methyl group from the alcohol, or you can get the propyl group from the alcohol. So let's first use the methyl group from the alkyl halide. Okay, so let's use CH3I from the alkyl halide. If you want, you can use a propyl group from the alkyl halide. Okay, they are both primary alkyl halides. They are both primary, so both these are correct. Okay, so if you use methyl iodide, okay, you have to give the propyl group from the alcohol. Okay, so the alkoxide will come from the alcohol. Okay, but if you used propyl iodide, the alcohol will be methanol. Okay, so both these will basically get you the end product. Okay, so that is how you do it. Okay, so you will get one R group from the alkyl halide, and you will get the other R group from the alkoxide ion. Okay, so this is, let's say, R1, this is R2. Okay, you can get R1 from the alcohol, and then you can get the R2 from the alkyl halide, or vice versa. Okay, as long as the alkyl halide is primary, we don't really care about anything else. Okay, so only requirement is that you have to have a primary alkyl halide. That is the only requirement. All right, so that is the first one. Okay, so the second one that we need is anisole. Okay, anisole is basically a methyl phenyl ether. So you have a phenyl group, and then you have a methyl group. Okay, so let's analyze this anisole. Let's analyze this anisole. Okay, so the R groups that we have is a phenyl group and a methyl group. Okay, so these are the two R groups that we have. We have a methyl group and a phenyl group. So if you wanna get the phenyl group from the alkyl halide, then it will not be a primary alkyl halide. So you have to get the methyl group from the alkyl halide. That is the important thing, because that is the only primary alkyl halide that we can use as the R group, as the R group. Okay, so for this reaction you don't have two different ways to do this. You don't have two different ways to do this. The only option that you have is to use CH3I as the alkyl halide, and then of course you will use benzene. You will use you will get the benzene from phenol. Okay, so alkoxide ion will be generated from phenol, and then this reaction will get you the product. Okay, so this is how you think about it. Okay, this phenyl group will not be a primary alkyl halide, so you couldn't use phenol. Okay, you couldn't get the phenyl group from an alkyl halide. So that is the only thing that you have to worry about. All right, so with that, I'm going to show you the answers, but they are basically the same things that I just mentioned. Okay, so for the first compound, methyl propyl ether, both methyl group and propyl group can be obtained by an alkyl halide. Both methyl group and propyl group can be obtained by an alkyl halide. Why? Because they are both primary alkyl halides. So which means the other R group can be obtained by an alkoxide ion. Okay, and the problem with anisole is that phenyl group will not be generated from a primary alkyl halide. So therefore the only alkyl halide that you could use is methyl bromide or methyl chloride. Okay, which is a primary alkyl halide. All right, so the next reaction that we are going to talk about, or this is actually the fourth reaction that we are talking about today, is alkoxymercuration of alkenes. Alkoxymercuration of alkenes. If you remember your alkene lesson, okay, alkene lesson, we talked about a similar reaction. Okay, so the similar reaction that we talked about is oxymercuration. The reaction that we talked about in alkene chemistry is the oxymercuration and deoxymercuration of alkenes. For that reaction, we used mercuric acetate and water in the first step, right? And in the second step we used sodium borohydride. We use sodium borohydride. Okay, so uh, what happens is that this was a Markovnikov addition. This was a Markovnikov addition. So basically, you are adding a hydrogen to the rich carbon. You are adding the hydrogen to the rich carbon, and then you are adding an OH group to the poor carbon. What is the rich carbon, if you ask? Okay, that is the sp2 hybridized, or the double bonded carbon with more hydrogens. We consider hydrogen as money. So if you have more hydrogens, you have more money. So you are a rich carbon. So according to Markovnikov rule, hydrogen tend to go to the carbon with more hydrogens, or the rich carbon. Okay, so rich gets richer according to Markovnikov rule. So hydrogen goes to the rich carbon, and then uh, poor carbon gets an OH. And the reaction alkoxymercuration for the synthesis of ethers is very similar. Very similar. You are using an alkene. You are using an alkene, of course. Okay, you are using an alkene. Okay, and then you are using a mercuric product, but you are not using acetate, but you use CF3CO2 twice as the mercuric compound. Okay, but rather than using water, the unique thing about this reaction is that we are using an alcohol. Okay, that is the important thing to remember. We are using an alcohol. That is important to remember. Okay, but here's the thing: the rest of the things are very similar to oxymercuration, deoxymercuration reaction. Okay, why? Because the alkene, of course, has, in this case, has a rich carbon and a poor carbon. Okay, note the number of hydrogens each carbon has. Rich carbon has 2 hydrogens, so of course that is the carbon that will get the hydrogen. Okay, see, the rich carbon got the hydrogen. Okay, and poor carbon got the alkoxy group. Poor carbon received the alkoxy group. Okay, so where did you get the alkoxy group from? It is from the alcohol. Okay, alcohol will provide the ether group. Okay, alkoxy group. All right, so this is also Markovnikov addition. Why? Rich gets richer, rich carbon gets the hydrogen, and the poor carbon receives the alkoxy group. Poor carbon gets the alkoxy group. So the only difference between this one and the oxymercuration is that we are using trifluoroacetate, salt of mercury. Okay, I mean, you can use mercuric acetate if you want. Okay, that will also give you the desired product, so that is not that different. Okay, but excuse me, but the most important thing is that we are using an alcohol. Alcohol is the compound or the reagent that will give you the ether group. Okay, or the oxygen and the second R group. So that is important to remember. Okay, here is a nice example. Here's a nice example. You have an alkene in here, cyclohexene, and then in here both carbons are similar because there is no rich carbon, no poor carbon. They are both similar. So one carbon gets the hydrogen. Okay, this is the carbon that received the hydrogen. Of course, you don't have to show it. And the other carbon received the R group from the alcohol. Okay, here is your alcohol, and that R group is going to the other carbon, and of course the oxygen as well. So alkoxy group is going to the other carbon. Very straightforward. Very straightforward. So as an exercise, let's see if you could do this one. All right, so I'm asking you to synthesize. I'm asking you to synthesize this. All right, so this is the this is the compound that I want you to synthesize. This is the ether that I am interested in. Okay, see if you could use let's say this is, let's make it a little bit more complicated. Okay, so there is no primary R group. Okay, so you couldn't use Williamson ether synthesis. So how do you make this one? How do you make this one? Of course, the better method will be to use the deoxymercuration. Okay, deoxymercuration. So first of all, what you need is you need to identify the R groups. Okay, so here is one R group, here is the other R group. Okay, let me use a different color for the two R groups. These are the two R groups. Okay, we can say this is R1 and the other one is R2. Okay, show me how to synthesize this ether using alkoxymercuration. All right, you can you can pause the video and try it, but I'm going to explain it to you right now. Okay, so you have two options. Let me get rid of the colors first. Okay, or maybe I should keep it. Okay, let's keep it. All right, so what you could do is you can get the R1 from let's say this alcohol. Okay, this is an alcohol that you could use. Okay, if this is the alcohol that you use, okay, then you might wanna pick the alkene like this. Let me change the color. All right, so here is the alkene that you will use. Okay, so you need this in your first one. Okay, so you can use mercuric acetate. Okay, and in the second step you need sodium borohydride, and of course one carbon gets the hydrogen. Let's say this carbon received the hydrogen. They're both equivalent. Okay, so it doesn't matter, and this carbon will get the alkoxy group. Okay, and then you will get your desired product. Okay, but there is another way to do this. Let's say R1 comes from the alkene. Okay, so let's get the alkene. So what I want to do is I want to use the same R group. Okay, but I want to have a double bond. I'm going to put the double bond right here. Okay, so here is my alkene. Okay, clearly in this one you have a rich carbon and a poor carbon. Now I don't have to tell you which one is rich, right? You know, so this is your rich one, this is your poor carbon. I mean, of course you don't have to label them in the exam. Okay, this is for you to understand the method. Okay, so then what will be the alcohol I need? Sorry, what will be the alcohol I need? Yes, so alcohol will provide the other R group, right? So all the other details are the same. I mean, second step needs sodium borohydride, and the first step also needs mercuric acetate. Okay, and then what is the alcohol that you need for the first step? Okay, so I'm going to erase all these common reagents so that I can have some space to write the material that I need. Okay, so the alcohol should provide the other R group, right? So the other R group. So I need this whole thing and the OH. This is the alcohol I need. right? And the hydrogen will go to the rich carbon, so that will be a CH3. This will be a CH3. This will be a CH3, and then CH3 group remains constant, and then I'm getting a new bond right here. I'm getting a new bond in the middle carbon, and then I get the alkoxy group. We get the alkoxy group from the alcohol. All right, so that is how you get it. That is how you get the answer. Okay, with that, I believe that you understand how this thing works. Okay, so this is a very important reaction, by the way. Okay, this is a very important reaction in organic chemistry. But if you remember oxymercuration, deoxymercuration, this is very similar. Only thing that you have to remember is this is Markovnikov addition. Markovnikov addition. Okay, that is something that you need to remember. With that, I'm going to ask you to do this worked example, okay, by yourself. Okay, in a second I will post the answers, or you might want to pause the video and then see if you could do it. Okay, so these are the solutions. Of course, I'm categorizing them starting from most reactive to least reactive. And we are interested in Williamson synthesis. Williamson synthesis, where it is an SN2 type synthesis. Okay, so you need a primary alkyl halide. Okay, so whenever you have a primary alkyl halide, the reaction is much faster. Okay, secondary alkyl halides are not that fast, and of course aryl halides are not reactive. Okay, so that is why ethyl bromide is the best or the most reactive alkyl halide. For B, it is also very similar. Okay, but you have two alkyl halides, but of course the ethyl bromide will be better because bromine is a better leaving group as compared to chlorine. Okay, but vinylic compounds are not reactive, so vinylic groups are not reactive, so that is the least reactive one. Okay, with that I'm going to conclude the video. Okay, so please look over the video multiple times if you feel like you need more practice, and of course do the quizzes from this chapter, and you will get a better understanding about these reactions. Okay, and also we discussed 4 reactions in this video, and don't forget to summarize them in your reaction book. Okay, have a good one, guys.